PowerPoint, just a marker and a whiteboard. All right? So our interest is in studying electron-molecule interactions. Why are we interested in doing that? Because when very high energy radiation interacts with matter, it produces huge quantities of low energy secondary electrons. And the hypothesis is that all of the damage done by high energy radiation can be attributed to the very low energy electrons, the low energy secondary electrons. So let's draw a graph here. I've shown this to you before, but so right here I'm going to plot, first I'm going to plot the number of electrons as a function of energy. Is it locked?
Yeah, it is.
Okay, can you unlock it, Frida, please?
How do I unlock it?
Just push one of those. Okay. So this is the number of electrons as a function of energy. This is the energy distribution of the secondary electrons. So what it's going to look like is something like this. And this energy here is about 10 eV. So most of the low energy electrons produced by the high energy radiation have an energy less than 10 eV. Okay? Now what I'm going to do is to plot on this same graph the probability of dissociating a molecule, a generic molecule, as a function of electron energy. Okay? And what you see is that that's what that looks like. So this red curve is the probability of dissociation. Okay, for any generic molecule, this is what you would typically see. Below 10 eV, there are what are called dissociative electron attachment resonances. At certain energies, the molecule can capture an electron, form a negative ion, and that negative ion can then dissociate, and therefore you're able to see that at energies below 10 eV, the molecule can dissociate. And I'll show you in a diagram very soon why these are resonances. Okay? At an energy around 10 eV, the dissociation probability begins to take off. 10 eV is approximately the ionization potential for almost every molecule that you can think of. You're going to be off by 1 or 2 eV if you say that the ionization energy of a molecule is 10 eV, any molecule. Okay? So what you see here is dissociative electron attachment. What you see here is ionization plus excitation. Okay, so these are the three mechanisms by which a molecule can fall apart when it interacts with electrons. Okay, so let's look at some examples of DEA. So if we were to pick a random molecule, okay, plus an electron, it's going to form a temporary negative ion, and that temporary negative ion can form NH2 minus plus H, or it can form NH2 radicals plus H minus. Okay, so this temporary negative ion, this NH3 minus, falls apart, and therefore the molecule dissociates. This occurs only at certain energies. That's why you have these resonances. Electron impact ionization is when you have NH3 plus an electron going to NH3 plus 2 electrons, and then this cation NH3 plus falls apart and forms NH2 plus a hydrogen, or it can form NH2 plus H plus. Okay, so the cation breaks apart and forms these species. This is exactly what is going on inside a mass spectrometer. Okay, it fragments, and therefore you're able to see these different species in the mass spectrometer, because the mass spectrometer allows only one positive ion to go through the quadrupole and strike the detector at a given time. Okay, and the third one, so this one takes place typically below 10 eV, but there have been some cases where it's been observed at energies as high as 17 eV. This one takes place at energies greater than 10 eV. And the third one is excitation, so NH3 plus an electron goes to NH3 excited state. The electron is still there, but it has now lost energy to the NH3 molecule. And this excited molecule can form NH2 plus H. It can also form something where it forms NH2 plus H minus. And this is called dipolar dissociation. So the excited molecule forms NH2 plus and H minus. To the best of my knowledge, nobody has really ever detected positive ions and negative ions in a single experiment for any molecule that shows conclusively that this mechanism is a viable mechanism for dissociating a molecule. So down the road, maybe this summer, we're going to look at dipolar dissociation. Our mass spectrometer is set up to observe both negatives and positives simultaneously in a single experiment. We've never tried that yet. Okay? So these are the three mechanisms by which a molecule interacting with an electron can fall apart. All right? So let me now draw a diagram that tries to explain why this is a resonance state. This is going to be a little bit tricky here. So this is the potential energy. This is the internuclear distance. Okay, you've seen this diagram in every chemistry course that you have taken. All right, this is for the neutral species. Okay. For the negative ion, so this is going to be AB minus, this is going to be AB, okay, and, oh, this is not a very nice diagram. Okay, so this is, remember, this is dissociative electron attachment. This is electron impact ionization. This is electron impact excitation. Okay, for dissociative electron attachment, what's going to happen is that you're going from the neutral molecule to the negative ion. Okay? So in your first PChem course, you will learn that there is something called the 0 point energy, and the molecule can really never go down in energy to this bottom of the vial here. It's the lowest energy possible is this amount here, and this is called the 0 point energy. Okay? And you will also learn in your physical chemistry course that when a molecule undergoes a transition, the transition is vertical. Anybody remember what that is called? I'm looking at Crystal. long time ago.
The energy transition is vertical?
Yeah.
There's a specific term for that?
Yeah. Okay, it's been 2 years since you took that course. That's okay. It's
I
called,
know that it does that.
it's called the Frank-Condon transition. Okay? Very important principle in physical chemistry. So, the nuclei are essentially stationary when a molecule goes from the ground state to an excited state, or when a molecule goes from one type to another type. Okay? So the green lines are supposed to be vertical. All right? And this is called the Frank-Condon region. Okay? So this is 0 here. Okay, so it's only electrons that have an energy between this value and this value, this electron energy, and this electron energy can cause the molecule to go from the neutral molecule to the negative ion. If the energy is lower, there is no transition. If the energy is higher, there is no transition. Okay, you have to be at the right energy, and that's why you have these resonances. Yes?
I had a question. When you were positioning, you were doing it to the left and to the right, but I thought the x-axis was internuclear distance.
I didn't specify what the internuclear distance axis. If you're talking about a diatomic molecule, the internuclear distance is always the z-axis.
Okay.
Okay, so this, I'm just saying R here, because this could be a polyatomic molecule, and this could be just the distance between two atoms within that molecule.
Okay.
But if you have a diatomic molecule, this would be Z. Okay? But for polyatomic molecules, there's no hard and fast rule about what label you give here. But it's important to realize that only electrons with certain energies cause this transition to form the negative ion. So if we were looking at the products here, these products here, as a function of electron energy, then you would find that the yield shows this resonance behavior. Okay? Questions? Yes?
So the green shaded rectangle,
Yeah.
that's responsible for one of the DEA pieces?
Right, just one, yes. Yeah, because there can be other negative ion states. So they have a different potential energy curve, and you'll have different energy required for the electron to make that transition. So I'm just showing you one of these.
Okay.
Okay? Thank you. Actually, this brings me back to this diagram here. So the red curve is the dissociation probability. The blue curve is the number of electrons. But if you're looking at the yield, how many product molecules are you going to get as a function of electron energy, then it's going to be a product of these two curves. You have to multiply the number of electrons by the probability, and then what you will get okay? Look at what happens here. Let's look at the high energy part of this. The red curve is saying that the probability for dissociation is increasing as you increase the energy. Okay? But look at what the green curve is saying. The yield of the radiolysis products at a high electron energy is almost zero. Why? Because the number of electrons, secondary electrons, with energies above 10 eV is almost zero. So here's the hypothesis. All of this is just theoretical graphs. Okay? Nobody has really gotten experimental data to prove this. And that's one of the goals of our experiments. Okay? We want to compare what goes on at very high energies with what goes on at very low energies, and see if we can bridge that gap, and see if we can explain everything that goes on at very high energies with just what goes on at energies below 10 eV. Questions? Yes?
So, when you initially bombard the thing with high energy electrons, do they turn into low energy electrons?
Exactly.
Okay,
Yeah,
so they're
yeah.
not there anymore. Or like
Right.
the high energy.
Yeah, it's converted. Yeah,
Okay.
it produces a cascade of very low energy electrons.
Okay.
Yes, Krista.
I'm just thinking about the experiments we've done in the last while. We're usually working above 10 eV, just slightly.
Yeah.
You know, between 10 and 20. So are we really showing anything, because it's using the same process as the high energy
Yeah, but
ionization?
we are. Your work has been 20 eV or below, right?
Right.
Yeah. When I say DEA is less than 10 eV, for methanol there is a resonance around 13 eV.
Okay. Yeah, I was just starting to get worried.
Yeah.
For a second.
So I'm talking about a generic molecule here.
Okay.
But we did some experiments at 900 eV, right? And those experiments are going to produce a cascade of low energy electrons. And the question is, can we relate the 900 eV data to the data that we obtain at 10 or 15 or 20 eV? Are they the same? You're one of the first people to do that type of experiment. Other questions? Yes?
Why, did you explain why, or could explain why you can't go to the bottom of the well in terms of the...
Oh, the 0 point, I will spend a lot of time explaining that when you take PCAM. Okay? It's called the 0 point energy. So purely quantum mechanical phenomena. Did she? Phone ring?
Food, yeah,
Is that the food?
I think.
Did you hear the phone ring?
Phone, well, she was on the phone. She didn't really pick it up, so
Oh.
either she's really
She's gonna
joking
fit.
or...
Food is here.
You want
Okay.
to talk to me?
Okay. Hello.
Sorry, please.
Hi, Song.